times the charge. So you're talking about the electron. So the charge times the probability density, and you integrate that over a given volume and differentiate that with respect to time. That would be real current, be like electronic current, like flow of electrons, equivalent, right? Okay. So J here's just your flux, your current. So you'll have these three values corresponding to the A term, the B term, and the C term. So in terms of your current densities, how much current per unit volume, in effect, you have these three terms. So B squared over A squared, and remember you got B over A, you calculated that it was this quantity here, and similarly for C over A here. So B squared over A squared, you interpret that's the fraction, your percentage, the fraction of the flux that gets reflected to the left at the step. The step is where the barrier starts. That's where the potential starts, right? So remember what A is, that's the amplitude of your wave function coming in from the left to the right, right? And B was your amplitude of the wave function moving from right to left. So the reflected wave, if you like. And remember one of the basic notions of quantum mechanics is superposition. You can add states, right? So you get one going this way, one wave function that way, you've got another wave function coming back. So at the same time, as quantum mechanics, you've got the state is somehow a sum of something that's moving to the right and something's moving to the left. I don't know if you've noticed, but increasingly as we get into the nitty-gritty, the formalism of quantum mechanics, we almost stopped talking about the interpretation of these things. But it's nice to remind you that your superposition in quantum mechanics is something truly weird, right? Okay. So anyway, so B squared over A squared is the fraction of your flux that gets reflected back, right? This quantity here, now we know C over A from here, so we can easily find, you just square it, get C squared over A squared. And if you multiply it by K dashed over K, that's the fraction that gets transmitted to the right. So it's the fraction of your incoming, if you like, it's a fraction of this, in a sense, of this wave function coming in from the left that gets transmitted, that goes through the barrier and keeps going. And that fraction is this. Now, current, just like in an electronic circuit, current is conserved. It doesn't disappear. It's sort of like an elastic fluid that it doesn't disappear. If you sum all of it, it remains, the total quantity remains the same. So these two fractions, the fraction that gets bounced back, and the fraction that gets transmitted, those two fractions have to equal 1. Okay. So again, for homework, prove that this, the fraction that's reflected, bounces back, plus the fraction that gets transmitted, that equals 1. So actually calculate that B squared over A squared plus K dash over K times C squared over A squared. Prove that that's equal to 1. Right? Given your values of C and A and B and A, which you know from here and here. Okay, so do that for homework. All right. Now flux is conserved. Think of it as like conservation of current in an electronic circuit. All the electrons coming in, they flow, left and right, whatever. So the total flows once they split still has to equal what it was coming in. It's conserved, right? So now you've got three 3 equations for A, B, and C. Here's your third one, right? And you have 2 others. You know, like here's an equation involving B and A, and here's another equation involving A and C. So you've got 1, 2, 3 equations for A, B, and C in terms of K and K dash. So solve those. I should do that. Okay, also homework. So solve for those A, B's and C's, and so R now, big R by definition, you have 3 bars, is defined to be the fraction that gets reflected, it gets bounced back at the barrier. So which was B squared over A squared. So actually solve for that. You know, get an actual value in terms of K and K dash, not involving A, B or C. Right? You've got 3 equations, you can solve for A, B and C, and therefore you know A and B, so you can calculate what this is, and you get this. So do that for homework. Right? And T, big T by definition, that's the percentage that gets transmitted, that goes through the barrier. Right? And that is this much. Okay? So you've solved for A, B and C, so plug in the values that you get for A and C into this expression and you'll get this. So prove that, do that for homework. Now these two fractions, they have to sum to 1, right? Now you can just almost by inspection, just by looking at it, you can see that's the case. Right? So if you add R and T, you've got this in common underneath, and you square this out, you'll get K squared minus 2K K dash plus K dash squared, and you add it to this, well that makes the minus 2K K dash become plus 2K K dash because of the 4 here, and what you're left with is K plus 2K K dash plus K dash squared, but that's just this all squared. So you got the same thing above and below, so 1, right? So R plus T is 1. That's pretty easy, right? Now, interestingly, when you know, in the case we're dealing with the case when the energy is larger than the potential barrier, so E is greater than V naught. Now, notice here. Look, this T is not 0, right? It's not, T is not 0. So, you know, some of it gets transmitted. You know, a certain percentage, in a manner of speaking, of your incoming wave goes through, right? So, you know, T is not 0. It doesn't. Your incoming wave doesn't all get bounced back. We'll do another case where that does happen, but not in the case when your energy is larger than V naught. Now, if your energy is much larger than V naught, like V naught's really small, and your incoming wave vehicle has very high energy. So if E is much larger, you know, this double arrow here means not just large. If it's just 1, that means larger than. But when you have 2, it means a lot larger than. You know, hugely. This is hugely greater than this. Well, then you get, you know, correspondence principle again. You get more or less the classical limit. You know, things start behaving the way they would in classical mechanics. Now, why is that? Well, if E is much greater than V naught, what does that mean? How can I deduce that? So if E is much greater than if E is much greater than V naught, so this, you can forget about this. So then your K dash just becomes K. K dash and K become almost the same thing. So if K and K dash are almost the same, this becomes nothing. So effectively your B becomes nothing. And what does that mean if B is nothing? That means the bouncing, the reflected wave is essentially zero, right? So almost none of it gets bounced back, which is sort of intuitively, that seems to make sense. If the barrier is so tiny compared to the energy of the incoming wave just goes right over the barrier as though it's almost not there. Okay, so almost none would get bounced back. So your B here would be zero, and that's a consequence of K dashed being almost equal to K, which you get from here. All right. Okay, so that's the end of the session. I will now have to lower the camera for the fourth quarter, the fourth session for this board.